Okay, so this is the last topic, the set building notation. So every set can be defined this way. Any condition that is specific enough to be verified and to determine whether a particular object satisfies it or does not, then it will produce a set. So every time you just test the condition, if it's satisfied, that element belongs to the set. It does not, it does not. So most typically when you deal with numbers, the sets are numerical. Then conditions are very typically are equations. Okay, so x squared is equal to 1 produces 2. The set becomes two numbers, -1 and 1. If you can carry out this computation, which is might not be necessary or maybe hard, but the point is the set is still there. You can represent the set in a number of different ways, and giving it by its set building notation is the simplest one. Okay, so then you could be required to do a lot of work to actually find out to find a list of elements like I did there. So x squared equal to 1. Okay, so that's great. So what does it sound like? It's give me all real numbers when squared produces 1. Okay, so that's what the set itself over here is. But then after some work, I discovered that it's a set consists of two elements, two numbers, -1 and 1. Okay, so and on. Every equation will produce a set in that manner. Some of them will contain one element, some two, maybe more, maybe none, that next line, or it might contain all the numbers that you have in mind. Next one is the same, the condition is an inequality. Okay, so that's at the bottom. So once again, you verify, for every number that is given to you, you might ask yourself, is it larger than 1 or not? If it is, then you put it on the list. If it is not, you do not. So that's how you, among the integers, you end up with that list over there, 1, 2, 3, and 4, and so on. Once again, verifying it one by one. If you try 0, it's not going to be on the list. Okay? So you can do it one by one, and you can see the pattern. So if you start with 1, 2, 3, it works out, and then you realize, well, if I keep going, that all of those numbers will be on the list, and that's what the ... means. Okay? The next line is more complex because there you cannot, even if you have infinite amount of time, you will not be able to verify every number one by one. So the next one, because we're talking about real numbers, and you keep zooming in on the real numbers, you get just as much as you had before. Okay, so that's the thing about solid objects. They don't have a finer structure. They have no structure. It's solid, and yeah, like I said, zooming in will produce the view you're going to get will be exactly the same as before. Okay, so that's why we described it at the simplest they're intervals. Okay, so sets like that are intervals. So x larger than or equal to 1. Well, every number to the right of 1 on the real line is in that set. So the real line that we take between -1 and infinity, made of these little pieces like that. Okay, and then that infinite interval or array is that set. So it's just the same set, just given in a different fashion. Okay, so and that's the interval notation. As a list, it is here. So there are a total of 6 8. 9 actually, interval notations. So these are the bounded intervals right here. So these are the bounded, a less than b, and they bound on one end it is bounded by a, on the other end by b, and that's the list. The other list is the list of infinite intervals, and so they are bounded only on one side. Okay, so that we already saw it here. So I could just fix it a little bit like this. So less than or equal to a, larger than or equal to a. So from everything from a to the left is included with a included or not including, depending on whether or not you have strict inequality or not. Okay, so and then so that gives you four more here. I have 2, but they have the same thing on the other end. And this is the ninth. This is the ninth interval, is this, which is the whole set of real numbers. Okay, so these are the 4 intervals. So the next topic is there's something to be said about these sets. Many things may be said about sets, and one of them is what is the largest element or the smallest element. So what is the largest element? Of a set. Okay, so as we can see that some of them very easy. So for example, the name of these two sets is maximum and minimum. Okay, so sometimes it's easy. Say max of a set 1, 2, 3, 7 is 7. Okay, minimum, MIN, of that set 1, 2, 3, 7 is 1. Okay, so if you put them in order, you know which one is the smallest, which one is the largest. So it's really uncomplicated. Okay, so but let's look at more complex situations that we have just considered with those sets. And how about the maximum of this set? Let's look at the minimum of this set. 1, 2, 3, 4, on and on. What's the minimum of this set? 1. What about maximum?
Doesn't the dot means it goes on to infinity?
Yeah, okay, it does. So the question, can you answer the question, what is the largest element of the set?
Infinity?
No, why not? Why infinity is not the answer?
It's not a number.
It's not a number, that's right. So not just it's not a number, it's not the element of the set. So if we want to speak of numbers or specific elements of the set, you're picking one that is on the list of the set. So so the answer is then you can either just write equal to infinity with the assumption, with the understanding that it is not a number, okay, or just say is infinite. So using words is fine. So notation is fine, equal to infinity. But it is what's behind it is something more complicated than in the next line. In the next line, we're saying that this minimum is a number. That number is 1. Okay. In the previous line, we're not saying that infinity is that number because infinity is not a number. Okay. We're saying that what's on the right is this maximum is infinite. Okay. So to begin with. Then there are even trickier situations. So how about the minimum of this set? Minimum of 1, 2. It is an interval between 1 and 2. Well, it is kind of 1, but not quite. Well, why is 1? It would not be quite a good answer.
Because it's inside the law of a bracket.
Yeah, and which means what? It means that 1 does not belong to the set. Okay, so then because it's not because 1 is not an element of the set. So why do we care about this part so much? For one, remember that the problem of that farmer and his fencing and his enclosure was we were doing optimization and we were looking for the largest possible enclosure. Okay, and so then you want to find the largest possible enclosure rather than enclosure that is just large, but he cannot build it. So if you have a scope of possibilities, within that scope, you need to find the largest value. So that's why the word maximum does not apply here. There will be another word that does, and we'll talk about that later. We'll take the simplest situation when it is possible to answer the question in the affirmative. So not only what is it, but rather the first question, is there is there? That would be a good way to put, is there the largest or largest smallest element of a set? So that would be really the good way to start, rather than before trying to find something, you decide if such a thing makes sense in the first place. Okay, so let me define in such a way that it does, even though it might not always be available. Okay, so given a set X, so suppose X is a set of real numbers. Then the minimum of X is an element of X, an element, say, A of X, such that A is less than or equal to X for each X in X. Okay? So that's the definition. A minimum is an element that is smaller or equal to every element in X. So that you can see how it applies over here. So 1 is less than or equal to every element in the set, which is 1, 2, 3, and 7. Okay? So similarly, the maximum of X, the inequality will be opposite, that's all, is an element A. How about B? B of X, such that B is larger than or equal to X for each X in X. Okay, so once again, that previous line over here, the set is 1, 2, 3, 7. The element that is larger than or equal to each one of them is 7. The only thing that you might worry about if you were really sticky is the language that we use very carefully. If you look at the grammar, the condition itself does not on its own indicate that there is only one such element. So on one hand, we are speaking of the minimum and the maximum, but on the other hand, the condition itself does not imply directly or immediately that there is only such an element. There is only one such an element. But fortunately, just looking at these examples, we can at least convince ourselves that there cannot be two maximum elements. Okay, so, well, at least among numbers. Okay, you can think of situations when even though things are ordered, there might be more than one maximum element. But when these are real numbers, then we are fine, and so there is only one. So there is only one. Only one of each, and this is a crucial part, or less. So it is possible that there is no such thing. With the example that we just looked at, interval 1, 2 does not have a minimum element, does not have a maximum element. So even though 1 is a good candidate, it is not a minimum maximum. Where it does work out is minimum of a closed interval 1, 2 is 1, and closed meaning that 1 and 2 are included, and a maximum of 1, 2 is 2. Okay, so when we have brackets, the endpoints are included, and those two endpoints serve as the maximum minimum points. So I don't want to give you the impression that we somehow have to deal only with intervals. So you can have any element of any nature, maybe like this interval, and then another interval, and then there is a point here. So say -1, 0, well, say 3, 4, 5, and 6. So that would be my set X over here. And it's not an interval, it's made of several intervals and then a point. And so maximum of X is 6. Maximum of X is 6 here. And minimum of X is -1. Okay? So, but some don't have minimum maximum points. So, so it is not uncommon, as you can see, to have a set that does not have a minimum maximum point. But to get on the right track, that is to figure out what do we do with those sets. So in what sense 1 is a minimum point, minimum in some sense of that interval 1, 2 when 1 is not included? We can look at bounds. Okay, so if we look at 1, 2, 1 is not the minimum because it does not belong, but it is a bound. Well, what I mean by that, it means that that inequality is still satisfied. So 1 is less than or equal to x for each x in x. Okay, so that's the good news, that the inequality can be satisfied. The only problem with choosing 1 as the minimum, it is that it does not belong to the set. Okay, that's the only problem. But otherwise, it is a very good bound for the elements of the set. Okay, but there are other bounds. Okay, so there are other bounds. Well, say 0 less than or equal to x for each x in x. Okay, and then in negative 1, 2, and then there are a bunch of these numbers. They're all bounds. In fact, we can then step to the other side, and we discover that x is less than or equal to, say, 2 for each x. So if these are called lower bounds, these are called upper bounds. Okay, so x is less than or equal to 2, x is less than or equal to 3, and so on. We have a bunch of upper bounds. So if you want to look at this set, which runs between 1 and 2, like this, then I have my, say, any number here, including 1. All of these are lower bounds. Everything to the left of 1, including 1, are lower bounds, and the upper bounds are these. Any number. Okay. So let me define this more precisely, and then, well, we already almost defined it, so let me define it first. And then we'll see why is it important. Okay, so once again, we suppose x is a set of real numbers. Okay, then a lower bound a of x is any number, not necessarily the one that belongs to x, so maybe outside of x, that satisfies that inequality. So a is less than or equal to x for each x. Okay, so that's the lower bound. So once again, well, the picture is, I think, tells you what's going on. And an upper bound b of x is any, how about I use capitals here? So a and b. So these are a's, lower bounds, and these are b's, upper bounds. Okay, so what is it? It is any number, once again, which might lie outside of x, that satisfies b larger than or equal to x for each x. Okay, so it's nice to remember the definition because it might be used, and as I mentioned that example of trying to maximize the enclosure. We are more interested in optimization of functions, right? Finding their largest values, but how do we find? In what sense we find maximum minimum of functions? That in this sense. So out of all possible outputs of a function, we find the largest one. So the outputs of a function form a set, and in that set we find the largest value, and that gives us the largest value of the function. Okay, in that sense. Okay, so you don't have to. It's not necessarily something more complex than that. So it's all just about real numbers, and this is how they're spread out. More examples would be if my set looks like this, then so it's infinite. Then what does it mean? I still have my lower bounds. And it's possible that I have no upper bounds. Okay, so that's the way. Remember, say it might be from 1 to infinity. It has lower bounds, it does not have upper bounds, or vice versa, right? So I might have something like this, and my set looks like that. Okay, I have a bunch of upper bounds, all of these, and no lower bounds. Okay, but they don't have to be, the set could have gaps. So another example of a set with no upper bounds would be what? How about this? It just goes to infinity. So say 1, 2, 3, 4. Once again, no upper bounds. Okay, so same with lower bounds. One set that has no upper bounds nor lower bounds is either, well, the integers or the reals, because they go to infinity in one direction and to infinity the other direction, so there are no bounds. Okay, so a set with both upper and lower bounds is called bounded. Okay, so once again, something that you'd expect to see from a set. So that is the confirms our classification of the intervals, bounded intervals between A and B. Okay, a bunch of them, 4 of them, and then those rays, also 4 of them, are unbounded. Okay, so otherwise unbounded. Okay, so that's a way to deal with what? With infinities. Okay, so that's what unbounded set is. It is kind of goes towards infinity, one or the other. Okay, so at least we know which ones are we do or do not have to worry about going too far to infinity. So if the set is bounded, then it has bounds on both sets, and the numbers then are limited in size. Let's put it this way. Okay, you can do actually a lot with nothing but bounded sets because you can imagine that the universe is bounded. Who knows? Well, some theories say that it goes on forever. Maybe it doesn't. Maybe it goes like this. The universe circles on itself, like this, and we're here. So we're looking in this direction, that direction, and it is just so far to see. But if we could, I'm looking in that direction, and I can see the back of my head. Well, so if that's the case, well, then the universe is bounded. It could be bounded. So certainly nothing in physics that, as far as I know, tells us that it cannot be bounded. Okay, it is not bounded in the same sense as we have discussed, because as you can see, it sort of circles on itself, but still the idea is the same. So all the distances are bounded, or all the sizes are bounded. So there are no infinities, not literally. Okay, so with that conveniently available. We are progressing to the next topic, and that is the Cartesian plane. Okay, so the Cartesian plane, you may have seen it before, but I want to take the right angle from the beginning so that there would be no confusion. The Cartesian planes is what contains graphs. Okay, so even though originally it's possible, maybe not positive, it appeared to, Cartesian plane appeared to, in order to study the geometry of the plane. So there's Euclidean geometry, all the triangles, lines, circles, and they intersect and all, and then you put it on top of a Cartesian coordinate system, and then you can study it this way. But our main interest is functions, so it is in fact then where the a function would live. So suppose f is a numerical function. Man, what? Numerical. So at its simplest, it is defined on the domain is R, and the codomain is R. Okay, so as you can see, we are where we are. We are facing two sets. Both of them are our real line, so both of them are real line. But it's not the same line. So even though it's made of the same numbers, but we can say, in a sense, for a matter of convenience, more than just the convenience, to say that these are two different copies of the same line. Okay, so I put it like this. This is my domain, X, and then I have my codomain, Y. Okay? So they're different. So it's easier to think of numbers, they come from the same source. Okay, that makes sense until you start doing functions, and then you have domain and you have codomain, and anything, especially if you step away from the abstraction and look at real life, then you have, for example, as we talked about motion, then X could be time and Y could be location. So even though both of them are numbers, they're really very different numbers, and the units are different. So X is measured in seconds, and Y is measured in feet. Okay, so that's why it is imperative to keep them apart. Okay, so then so once again, domain and codomain are two axes. You remember what they come with? They come with the origin. Okay, the origin and the unit. Okay, the other one also comes with the origin and the unit, which could be different. So intentionally I put that one elsewhere so they wouldn't think that even though it's the same copy of the same real line, that the units somehow match up. They don't have to match up. Okay, and then if you remember how we progressed, what function is, it is correspondence from x to y. So for x's are the inputs, y are the outputs, and so this is how I can visualize it. If I just put them maybe side by side, well, or not. Let me put it this way. So this is my x, and this is my, I just need more room here, and I have my y here. So I remember how we did it. We put arrows everywhere. So if I have a bunch of marks on the x-axis, a bunch of marks on the y-axis, so 0, 1, 2, 3, -1, -2, -3. I have my marks also on the y-axis, 0, 1, 2, -1, -2. So then what we are dealing with here is a correspondence between x's and y's, from x's to y. So every entry on the x in the x set has a corresponding entry on the y-axis. So for example, you can do it like this. So 0 goes to 1, 1 goes to 2 maybe, -1 goes to maybe also -1, -2 also goes to -1, something like this. That doesn't matter what this is. There is some kind of correspondence like this. And then every value in between might also go somewhere, once again, depends on the circumstance. So that is my F, okay, the correspondence. Okay, of x's into y's. Inputs here in red, and in green are the outputs. Okay, so once again we're studying functions, and then what we already did with the tables. Remember those tables that eventually produced tables of values. I guess let me just go in and find that. Let me find that picture. Let's do this. So this is my function, and remember how we proceeded. We created a table. So from arrows, we put the two sets along the two axes, x and y, green in the opposite color, unfortunately. And that creates a table. So if Tom likes basketball, so we put a cross on it. And then we progress to graphs. The only thing that is different, we are putting the x-axis horizontal and the y-axis vertical. So let's go straight to graphs to point out what we're looking at. So I am putting the x-axis horizontally. Okay, I'm putting the y-axis vertically. It is what this is. It is a kind of a table of values that in each column there will be one entry. So once again, let me. It is typical, which is what you're observing here. It is typical, but not required to have the zeros aligned. So one copy of x and x's. Well, let's see. Perfect. Okay, so one axis. So let's be literal here. So one axis, this is say the x-axis, and it has a 0 somewhere here. Okay, then there is the other axis. Okay, and they live apart, and then there's that correspondence. Well, before you get to the correspondence, what you get is how do I align these two? I don't want to align them like that because that's meaningless. I align them like this. Okay, and I take the origin of the first and the origin of the second and put them together. Okay, and that creates the origin of the plane. Okay, so that's to begin with. Before we even get to the function, we align the zeros. So I let me put it this way: 0, the 0 of the y-axis, and the 0 of the x-axis, like this. Okay, so that is a very special point because there are 2 points like that. As I said, it's not required, and you frequently see outside of mathematics, especially when they are not aligned, zeros are not aligned. In fact, probably I can show you on how Excel does it. Perfect. Well, this one is aligned. I need to one that's not aligned. Well, let me change something. How about I put here 3. Oops. Okay, as you can see, okay, well, I'm sorry. Since I'm doing it, well, let me go straight to the settings, and okay, it is settings, and where those settings are is impossible to find now. Move. Well, you just have to take horizontal axis. Okay, so it doesn't have to start with 0. It could start with something else. Okay, I don't know how I edit it. New version. Changing everything. Anyway, so just take my word for it. They do not have to be aligned, especially in Excel or in any other place. I'll just have an example later on when that actually happens. So, but suppose we do align them, which is typical in mathematics. I am plotting my points the way I have. So once again, -1, -2, -3, 1, 2, 3, and 4. Y units are bigger, So this is 1, this is 2, this is 3, okay, -1, -2, okay, so, and then for each arrow there is one dot. There will be one dot of the graph. Okay, so 0 goes to 1, so this is one dot. 0 goes to 1. Look at it. On the x-axis, I'm looking at 0. On the y-axis, I'm looking at 1. So these are the two elements I'm looking at, and it creates one dot on my graph. Okay, 1 corresponds to 1, so another point right here. I'm starting at the center, and I'm moving to the right. Okay, I probably should start from all the way from the left. I'm starting from the middle. 0 goes to 1, 1 goes to 1, 2. So I have 2 points already. And then 2 goes to, hold on, I messed it up. Sorry about that. 1 goes to 2, right? 1 goes to 2. Thank you. 1 goes to 2. 2 also goes to 2. So over here, another point, another dot on the graph. And then 3 goes to, say, 4, maybe. No, 3 goes to 3 maybe, like this. Okay, so one more dot on the graph. To the left, -1 and -2 both go to -1. So these are the two dots. And -3 goes to -2 like this. Okay, so that's the graph. This graph is complete if our domain is these numbers. So let me make that point clear. So it's complete if the domain is the set that we see, -3, -2, ... to 3. So if it goes from -3 to 3, then we don't need anything else. These points is it. It's not only the visualization of the function, it is pretty much the function. So we can get the whole function from these dots. Okay, it is when there is a more complexity, and every element between these might be a possible input. These are also might be possible inputs. Then there will be more dots. Each of these points will go somewhere, and there will be dots here somewhere. We don't know. Okay, so the graph might be then, as a result, might be a curve. Maybe there might be infinitely many points, and if there are enough of them, they might sort of merge together into what might be a curve. Okay, so that's how we create. We automatically have created at the same time we created Cartesian plane, and we have created the graphical function. So that's why we care. We care about it because we want to have plot graphs. Okay. And but let's look at let's forget about the graph for a moment and just look at what's that we have. So what happens if we remove the dots? Okay, so this is my graph. Okay, so this is my Cartesian plane. I'm going to erase this. Okay, so there are no functions. Okay, no function, no dots, only the two x's. So what is so special about it? So let me repeat: two copies, possibly different copies of the real numbers. Okay, in fact, they don't have to be real numbers entirely. They could be. Remember, we talked about real numbers as this solid thing with no interruptions, no cuts, no missing points. Or we could also speak of a ruler that have marks, and those markings is the only thing we care about. So whatever in between is ignored. So if you have on your ruler up to 1/16 of an inch, that's it. So in between there is nothing there. Okay. So either way, this construction works equally. Okay. So in this particular case, let's suppose we have real numbers. So every interval does not missing any points between 1 and 2, 2 and 3, and so on. Okay. So what is that we have? What we just used? We have a bunch of we have markings on the x-axis and markings on the y-axis. but we also are able to find the markings for every other point on the plane as well. So for example, this is another point, and this point is 1, 1. Okay, 1, 1 meaning it is a location, also known as the coordinates of that point. So we express that location, this dot, as numerically. So that is the point of the Cartesian plane, is that every point on the plane can be expressed algebraically as a pair of numbers. Okay, so 1, 1, and every, like I said, every single one of them. So I just go vertically from each location like this. For the graph, I need only 1 point per x, but if I speak of, if there is no function, then every point is it might be needed at some point. Okay, so through each mark on the x-axis, I draw a vertical line. Through each mark on the y-axis, I draw a horizontal line. The x's are perpendicular to each other. Okay, so that's what makes it Cartesian, and the computations become simple. And these lines, horizontal lines, each horizontal line intersects each vertical line, producing a point. They intersect once and exactly once. Every vertical intersects every horizontal once, and that is telling you where it came from. So, for example, if I pick this point over here, I know that it has come. So, a point is say this is a location. Okay, if this is a location and I want to find its coordinates, what do? I look at on what lines it lies, and it lies on this line. Okay, which crosses the x-axis at 3, and I look at the other line, the horizontal line, it crosses it at 3 as well. So that location, looking at these two numbers, 3 and 3, combined together, give me the coordinates. So it is 3, 3. So that's the notation. Unfortunately, as you can see, the notation is exactly the same as the one for the integral. Right? So it's unfortunate. 3, 3 looks exactly like the integral from 3 to 3. So sorry about that, but that's just history, and we cannot change that. So the coordinates of is given as a pair of numbers in parentheses always. So parentheses, number, comma, parentheses, and the other number in parentheses. Okay, so so what is it? Parentheses, a number, comma, and the other number, and the other parentheses that closes it. Okay, so remember where these numbers come from. This number comes from the x-axis, and this comes from the y-axis. Okay, so one from horizontal, one from vertical. Okay, I hope you can see that these are not squares, so I did not do it by mistake, but by choice, that we cut the plane into rectangles. Okay, so once again, if we speak of functions, we are not really studying the geometry of the plane. So this is not like a map. You know, if you see a map of the Earth or any spot, then they cut it into squares, because horizontal and vertical should be measured the same way. You don't want to mess with that. Well, actually, there is an exception, I suppose. I think, well, maybe when airplanes, you measure, airplane is approaching a destination, then at the airport, they measure the distance in miles, but altitude in feet. Okay, so it's possible, even though you are doing geometry, you have two variables, or three in this case, and both of them are spatial variables, with special spatial measurements. You might be using different units, so you can mess it up, but that's really how it's done historically. Distance is in miles, and altitude is in feet. Okay, so that's not entirely unusual. But if you speak of functions, then definitely the x's and y's have nothing to do with each other. There's dependence of X would be time, and then any quantity might depend on time, that's Y. Or the X, both of them can be, X is location and Y is the temperature. Okay, so you're traveling, and at every different location, you measure the temperature, put it, and you have a function. So once again, X's and Y's are unrelated. Okay, so let me review this one more time so that you can see how what I just explained with drawing appears on the with Excel. So the things is exactly the same, except they usually, it does not appear automatically, but rather appears based on the data that you submit. So if you submit this data of a function, of values of X in the first column, values of Y in the second column, they are paired up, and then it plots every point on the x-axis, and it automatically chooses the appropriate alignment of appropriate units for the x-axis, as well as markings, and the same for the y-axis. But you can change that as well. So in this particular case, as you can see, it has chosen to have the units to be, well, the units are still 1, 2, 3, 4, but the markings go 0 and 2. So it skips 1. So you certainly should be surprised, not be surprised by that. And it never goes to negative numbers. Why not? Because, well, there are no negative values of x in the domain. The domain starts at 3, and so all of these are positive numbers, and the happen to be integers, but the output numbers are the y's. Okay, so the homework will include this and probably a couple of things from last week. Okay.